Okay, so uh, okay, so today we're going to finish up this stuff on sequences of numbers, limits of sequences. Okay, and maybe one way to start off is to think about this sequence. Okay, so does anyone know what the square root of 2? Does anyone know the first few digits of the square root of 2?
1.41.
Yeah, 1.41. Great. So if we look at 1, 1.4, 1.41, 1.414, 1.41442, blah blah blah, right? Then this is a sequence, right? This is a sequence, and doesn't mean you know the square root of 2. Know that this is tending towards, this is getting closer and closer to the square root of 2. Okay. But if again, sort of going back to the rational numbers, if we were in the rational numbers, what is the limit of the sequence? Is there a limit of the sequence? Or right? There's actually no number that this sequence is tending towards, right? It looks like it's tending towards a limit, but there's actually no rational number that works as the limit of this as the limit of the sequence. Okay. Now for the real numbers, it turns out that if you keep on going, this actually tends towards a number, and that number is a real number, which we call the square root of 2. Okay. So yeah. Just for fun, let me ask you to consider this. If I look at 1 plus a half, 1 plus a half plus a third, 1 plus a half plus a third plus a fourth, etc., what do you think happens to that? Do you think that will tend to some limit? Does anyone know what happens to this? Things that you're adding on to it get smaller and smaller.
So wouldn't it tend towards 2?
I think it tends towards 2. It tends towards 2. Any other guesses? It doesn't really matter. You can make some crazy guess. Yeah.
Does it tend toward 1?
Does it tend toward 1? That's a crazy guess. Okay. It couldn't, right? Because as you see, it gets past 1 from the very beginning. Right. 1, 1.5, 1.5.
But I guess my thought process was that what you're adding gets smaller, closer and closer to 0.
That's true, but you're adding it on top of what was there before, right? So if it were like this, 1 plus a half, 1 plus a third, 1 plus a fourth, then that would tend towards 1, right? Because you're looking at 1 plus 1 over n as n goes to infinity, right? But here what we're looking at is 1 plus 1 half plus 1 third plus 1 over n as n goes to infinity, right? So the number of terms is increasing at the same time. We're not just adding on 1 term, but we're adding n terms total. Okay. Does anyone know what happens to this? Yeah, Kelly.
Infinity?
It turns out to be infinity. Yeah. So it turns out that even though the things that you're adding on get smaller and smaller, turns out that this sequence will tend towards infinity. This is a famous sequence called the Harmonic Series. There's a related sequence: 1 plus a half squared, 1 plus a half squared plus a third squared, blah blah blah. Does anyone know what happens to this one? I'll be shocked if you know what happens to this one. What do you think? Well, now the things we're adding on are small. In fact, they're smaller than what we had before, right? Right. 1 half squared is something smaller than a half. 1 third squared is something smaller than a third. Right? The things that we're adding on are shrinking at a faster rate than the ones we have here. So what do you think is going to happen? Will it be finite, or will it still be infinite? What?
Wouldn't it still be infinite?
Still be infinite? Anybody else? Right. It turns out that these things are shrinking fast enough that that what you get is something finite. In fact, you get something really wonderful, which is pi squared over 6. It tends towards pi squared over 6. But in calculus 2, you'll see why this happens, but you won't see why it turns into pi squared over 6. To see that, you'll have to wait until a later course. Okay. But anyway, just to sort of get you a little curious about what we're about to talk about. Okay. So what we're talking about today, what we're starting off today, is something called a geometric series. Okay. So a geometric series is something like this. It's a series of the form, it's a sequence of the form 1 plus r, 1 plus r squared, 1 plus r squared, 1 plus r squared plus r cubed, 1 plus r squared plus r cubed plus r to the fourth, etc., etc. Okay. So you're adding, an increasing number of terms, right? And the terms that you're adding are all multiples, all powers of r, right? R to the 0, r to the 0 plus r to the 1, r to the 0 plus 1, r to the 1 plus r squared, etc., etc. You're adding powers of r, right? So let's say that this is a0, a1, a2, a3. Okay. So geometric series, a geometric series is a sequence. Is a sequence a sub n where a sub n is 1 plus r plus r to the n minus 1 for some fixed r. From some fixed r, some fixed r, a real number. Okay. So it's something that looks like this. Okay. If r is 1, then what does your sequence look like? Suppose r is 1. Well, what does your sequence look like? It'll be, the first term will be 1, the second term will be 2, the third term will be, will be 3, the fourth term will be 4, etc., etc. Right? So in that case, your sequence, if r is 1, then it's sort of a boring sequence, 1, 2, 3, 4, 5, 6, 7, and it diverges. Right? Right. So notice that, so dumb comment, if r equals 1, then a sub n is n. Right? Right. And maybe I should change the numbering here so that it's in line with my notation there. Okay, so I'm going to change the numbering here so that a sub 1 is the first guy. Okay?
Wait, you said it diverges?
Yeah, it diverges because it goes to infinity. Well, it converges to infinity.
Okay.
Yeah, sorry.
Wait, so sorry, can you explain diverges then?
Sorry. So I should, sometimes people call sequences that go to infinity divergent.
Okay.
Okay, but it also makes sense. It would also make sense to say that this sequence converges to infinity.
Okay.
Yeah. Yeah. So divergent. This term divergent sort of encompasses no limit or limit is infinite.
Is that the only way that the term diverges is used?
Yeah. Okay. And in that case, the limit is infinite. Okay. In that case, if we're in the simple case when r is 1, then the sequence goes off to infinity. Okay. However, let's say that r is a half, right? Then a1 is 1, a2 is 1 and a half, a3 is what? 1 plus a half plus half squared, etc. And what happens to this sequence? Does anyone know what happens to this sequence? Can anyone guess what happens to the sequence?
Which is, no, 0? Well, internal is being added.
Is it also done on
0, infinity. Megan?
Is it 10 equals 2?
2 is actually the answer.
Okay.
2 is actually the answer. This is related to Zeno's paradox, right? Which came up earlier. Like does time stop when the genies go crazy, right? Right. So if you look at this, right? I'll draw it vertically. Right. A1 is 1. A2. So here's 1 and here's 2. A1 is 1. A2 is 1 plus a half. Right. That's A2. 1 and a half. A3 is 1 plus a half plus a quarter, right? Which is half of the remaining distance, right? Half of the remaining distance. So that's A3. 1 plus a half, right? 1 plus a half plus a quarter, right? And then you add on an eighth, you add on a 16th, blah, blah, blah. And you see what's happening, right? With each time you have the distance to 2, and in the limit's actually going to be 2. At least it seems like it's going to be 2, right? So it seems like the limit exists. And it's 2. Okay. So what we're going to do is think about that a little bit more precisely. Rather than saying, it seems like it's 2, let's think about why it actually is 2. Okay. So, in fact, it is. So here's the theorem. It says it's this. The first part has 2 parts. 1 plus r squared plus r to the n minus 1 actually is r to the n minus 1 over r minus 1. And then the second one is that if the absolute value of r is less than 1, then the limit of 1 plus r to the n minus 1, as n goes to infinity, is 1 over 1 minus r. Okay, so for example, right, if we're looking at if r is a half, and we're looking at this Zeno's paradox thing, then what the second statement says is that, well, you've got something of size less than 1, the limit is going to be 1 over 1 minus r, right? So the limit of 1 plus a half squared plus a half to the n minus 1 as n goes to infinity is going to be 1 over 1 minus a half, which is 2. Yeah?
Why do you have the n minus 1 instead of n?
That's just, it doesn't, we could have done it with n, we're going to do it with n minus 1. It'll be convenient in a second, you'll see why. Yeah, it's just a convenience, but we could have done it just as well the other way. Okay. So this turns out to be 2, right? If I asked you, say, what's 1 plus a third squared plus a third to the n minus 1 as n goes to infinity. What's the answer?
1/6 or 1 2/3.
What's it going to be? So it's going to be 1 over 1 minus a third. Right? So 1 over 2/3, in other words, 3/2. Maybe 3/2. Is that okay? Everyone all right? Okay. If I ask you, what is 1 plus a tenth plus a tenth squared plus etc. as n goes to infinity, what is it? 10 over 9. It's going to be 1 over 1 minus a tenth, like 1 over 9 tenths. Let's just say 10 ninths. Right? If I asked you what is 9 plus 9 tenths plus 9 9 hundredths plus etc. What if I asked you that? This is a little bit different. Hold. Okay, think about it. Think about it for 1 minute. I'll be back. What's the answer? Stefano?
10 over 81.
10 over 81? Priya? What?
10. 10. Just 10.
10? Anyone else? Okay, the answer is 1. Oh wait, it's 10. I'm sorry. Yeah, it's 10. Right, because it's 9 times the other guy. Right? If I pull out the 9 here, then I get if I factor out a 9 from this, right, this is the same thing as 9 times the previous one. Right, which was 10 ninths. This is 10. Okay. Yes, madam.
Is it mathematically sound then to just say R is 9/10 and then do like 1 over?
It's not. It's not.
Or just
So
between
R
the
isn't. So yeah, the trouble is that for this to be a geometric series, it really has to be that everything is a power of some R, right? But these things aren't powers of 9/10, right? These things aren't powers of 9/10, right? This is not a power of. If the 9 were inside here, if the 9s were all inside, then yeah,
Okay.
then that would be a geometric series.
somehow it just conveniently works out that like it did work. Like I said the R is 9/10, but I think it's probably just like the problem. Like it probably wouldn't work for another one. But somehow-
Yeah, it shouldn't work out like that, right? Yeah. Yeah. Okay. Okay. What if I actually the one I wanted to do, the reason I got confused is because I actually wanted to multiply this thing by not by 9 but by 9/10. If I multiplied it by 9/10, right? Suppose I had this 9/10 plus 9 over 10 squared plus 9 over 10 cubed plus like, as 10 goes to infinity. What would that be?
In that case, what is R? But you're taking out the 1?
Yeah, so it's a little bit trickier looking, but it's still the same thing. Still the same thing. You can recognize this if I factor out a 9/10, then you see what's left over, right? I get 1 plus 1 over 10 plus 1 over 10 squared plus 1 over 10 to the n minus 1. Right? If I factor out a 9/10, then I do have a geometric series left over. Okay, and that geometric series goes to 10/9, right? As we calculated on top, right? So this is going to be 1. Yes, Stefan.
I said 10 over 81 because for some reason I got confused with the theorem you gave with the 1 over 1 minus r.
Mhm.
So I thought it was like the first part minus r. It's always 1, like regardless of what the geometric series is. As long as the geometric series starts with 1.
In the numerator?
So
To find
here,
Hmm?
we were talking about this one.
Yeah.
Okay.
So like if you're trying to find the limit,
Mhm.
you can use that theorem, and it's always 1 over 1 minus r.
Yeah, but this isn't a geometric series.
Exactly. So
Yeah.
you have to like make a geometric series.
You have to make it look like a
And
geometric
then you can
series.
use that.
Yeah. So you're combining your knowledge of multiplication with your knowledge of you're combining your knowledge of distribution, right? You're distributing, right? So you pull out the 9, and then you're left with a geometric series.
Okay.
And you use your new knowledge about the geometric series to say, oh, this is just 10/9. So the point of yeah, Claire.
When you took out the 9,
Yeah.
the 9/10 from the bottom one, wouldn't it be, well, because isn't it the squared have to be for 9/10 the whole thing squared instead of just the 10 squared?
If I pull out 9/10, if
Yeah.
I factor out a 9/10 out of this thing, right, it's going to be 9/10 times 1 plus 1 over 10, right, because this is 9 over 10 squared. Right, so I get 9 over 10 squared. Plus
Oh,
9
okay,
over
sorry, yeah,
10
okay. I
squared.
thought you did 9 over 10, and that makes sense.
Uh-huh.
But that makes sense.
Part of the point of this is to give some meaning to this thing, this sort of thing, which if you write it, it's it's 9, 0.9, 0.99, 0.999, 0.99999, 0.99999, etc., right? So this is something that you've seen before, right? 0.9 repeating. Right? But maybe at that time you didn't realize that it was an infinite, it was, what we're talking about here is actually the limit of an infinite sequence. Okay, now you know. This thing is an infinite sequence. What it means, what's its meaning? 1. Right? What does it mean? 1. Okay. Right. So yeah, when you're a kid, you see these things like, oh yeah, it's just 9 repeating forever, but you don't really think about what it actually means. Now I hope you have some sense of what it actually means.
On the whole model, should we n minus 1 or n minus 2?
n minus 2 because I factored out a 10 here.
Oh, you have a minus 1 to the top one.
Sorry.
Okay.
Yeah. But even so, as n goes to infinity, this is going to go to 10 over 9. Because it's still the same. It's still the same sequence. It's still the same sequence as this one. It's just one behind. But the limit is going to be still the same thing. Right? It's like I have one sequence, and then I have another sequence that goes a little bit faster. Right? They're still going to have the same limit, right? Even though one guy is starting later. This one is starting later than that one. Everyone okay? So, geometric series. Geometric series. Probably the important one is the second one. Although the first one is kind of important too. So let's talk about both. Okay. So let's think about it. What's going on? Why does this happen? So let's consider 1 plus r, 1 plus r squared plus r to the n minus 1, right? And let's call that thing s. Okay, s for sum. Okay, we're trying to figure out what the sum is. Maybe I'll call it s of n for the sum of n terms. Okay. Okay. What happens if I multiply that thing by r? What do I get? Everything will be raised by a power, right? I'm going to get r plus r squared plus r to the n plus r to the n minus 1 plus r to the n, right? If I multiply everything by r, the 1 becomes an r, the r becomes an r squared, the r squared becomes an r cubed, the r to the n minus 1 becomes the r to the n. Right? Okay. So now I'm going to subtract. We're trying to figure out what s of n is, right? Our goal is to figure out what is s of n. I think I may have it wrong over there, but we'll figure out what it is anyway. Okay. So what do you get? You get 1. What do you get? Well, subtracting the bottom from the top, you see you get 1 minus r to the n, and on the right-hand side you get s of n minus r s of n. Sorry, I've got it wrong over here. But we'll figure it out and then we'll fill it in. Okay. So you get s of n, 1 minus r, equals 1 minus r to the n. And so what's s of n? To solve for it, right? 1 minus r to the n over 1 minus r. Okay, and that's what I should have had. Minus r to the n. So for example, right, if I ask you again, what's, say, 1 plus 1/3 plus 1/3 squared plus 1/3 to the 999. Here's a problem for you, right? What is that? What's this sum? Well, what we've just seen is that the sum of the first 1,000 terms is going to be Can somebody read it off for me? The sum of the first 1,000 terms is going to be 1 minus r. What's my r? 1/3. 1/3 to the 1,000 over 1 minus a third. Okay, so that's the sum right there. Just sum the 1,000 terms using this formula. Clear?
So A works for anything that falls under the category of B2.
Yeah, A works for any number, except for r equals 1.
Okay.
Yeah. So A works for any r not equal to 1, and then B works for, so I could use a big number, right? Suppose I say what's 1 plus 3 plus 3 squared plus 3 to the 999. Well, let's just use the same thing. Your ratio r is 3 now, so you get 1 minus 3 to the 1,000 over minus 2.
So for any r less than 1, the top and the bottom will equal each other?
Yeah. Well, no.
Or A
no.
and B will equal each other? Because I don't understand what the difference is between them.
The difference is that here we're taking the limit as n goes to infinity.
Okay.
And in the upper one, we're not taking the limit, right? So here, in the upper one, we're talking about you're summing a finite number of terms. The first 1,000 terms,
Okay.
right? First 1,000 terms. So. Yeah. And it's infinite. Question?
No, you just answered.
Okay. Yeah, Kimai.
If R is greater than 1, is it possible to limit it, or is it
Well, if r is greater than 1, then what's going to happen here? You're going to be taking the sums of, every time you add on another term, it's going to be bigger than 1, so it'll head off towards infinity, right? Or if it's a negative number, then it's going to sort of bounce back and forth, right? So the thing that you're adding on will be greatly positive or greatly negative, and it's not going to have a limit either. So the only time you have hope is if r is smaller than 1 in size. Okay. So this is pretty cool. I hope you agree, right? If you were asked to sum the first 1,000 terms of this, as an elementary school student, right, it would take you a long time, but now you can do it immediately. Right, as punishment for being loud in class or something like that. Go sit in the corner and sum the first 1,000 terms of at the powers of 3, the first 1,000 powers of 3. Yes, Stefano, do it.
So A, it cannot equal 1. B has to be between 0 and 1.
Between negative 1 and 1.
Negative 1.
Right, because the absolute value has to be smaller.
Okay.
Yeah. The story is that, did I tell you the story? Maybe I did it already. That Gauss is, the great mathematician Gauss, when he was 8 years old, his class was noisy, and so the teacher said, everybody, be quiet and sum the numbers from 1 to 100, right? And so all the kids start summing the numbers from 1 to 100, but Gauss just sits there and looking up at the sky, right? And then after a minute, he writes something on his pad, hands it in, and he writes down the right answer. It's 5,050. Right. Right. So, but he didn't do it by adding, but he did it by some clever way, by either he figured out a formula or he solved some pattern. There's a formula. If you look at 1 plus 2 plus up to the n, it actually turned out to be n plus 1 over 2. Right. So maybe you could do it he could have done it that way. Who knows? Or
well, couldn't you do 1 plus 99
Yeah,
and
yeah.
find all the pairs?
Yeah. So there's another simpler way, which is to say, well, I know that 1 plus 99 is 100, right? 2 plus 98 is 100, et cetera, et cetera. And you figure out how many hundreds you've got. You've got the 50 left over, right? You got, et cetera, et cetera. So you get 5 or 5 out. Okay. Okay. probably not going to finish everything that I thought we'd do, but okay. Okay, I think we're good on geometric series at least. Okay, so here's the question. Like, remember earlier we were talking about this sequence of numbers, 1.4, 1.41, 1.4142, etc. Right. How do we know there is a limit in R for this sequence? How do we know there's a limit in R for this sequence? And what I'm going to give you right now isn't really an answer, but it sort of gives you a sense that we might know why there is an answer. Okay. Sorry. Here's something called the Monotonic Convergence theorem. Monotonic Convergence theorem. It basically says this: if a sequence is increasing and bounded above, if a sequence A sub n in R is increasing and bounded above, then the limit exists. It converges to some number in R. Okay. And similarly, if it's decreasing and bounded below, and when I say bounded above, what I mean is that there's a number where all the values of the sequence are less than that number. Okay. So there's some bounded above means there is there's a number m such that a sub n is smaller than or equal to m for all n. So there's some number that's bigger than all values.
Are the boundary and the limit always the same?
No, they need not be, because you could say, this one's limit is square root of 2, but you could say, I know this sequence is bounded by 2.
So the boundary can just be anything? Right?
Anything bigger than all the values.
Okay.
Yeah. But what turns out to be true is that the smallest number that works as a bound is the limit. Yeah. So, so this is really a statement about real numbers, that there's going to be something there at the end, right? There's going to be some number there that acts as the limit, whereas in the rational numbers, this doesn't happen. Okay, so we can't prove this. We're not going to prove this because this is really a subtle fact about the difference between real numbers and rational numbers. Okay, so we're not going to prove it. We're not going to prove it. Because this is again sort of a subtle fact, a deep fact that we could do, but it would take a while, like a month or so. Not a month, maybe. Well, maybe it would take at least a couple weeks. I'd say. Yeah.
So does that just mean that every function has a limit of infinity or a limit of a real number?
No.
As it goes to infinity.
No. It says any sequence. So what it says is that if you have an increasing sequence, it either goes to infinity or it has a limit. If you have an increasing sequence, yeah.
Okay.
Yeah.
Cool.
So I think that's what you were trying.
Yeah, that's what I was trying to say.
Yeah.
Function.
Yeah. So same way of saying any increasing sequence. Again, you got the right idea, but the words are not quite right. But good for the idea. any increasing sequence is either bounded above and contains a limit, or has a limit of infinity. Okay. Yes, ma'am.
Like, who decides the boundary? And, like, what's the point of it?
You don't. Nobody decides it, but you can guess it. You can figure it, right? Somebody gives you this sequence,
So there
right?
are unique boundaries, like sequences.
Say it again.
Like, so there's a boundary that you have to, like, solve for, sort of?
Well, so it's like this. If somebody gives you this sequence 414, 1.4142, and says, here's this sequence, and every time I'm going to add on a new digit here. Every time I'm going to add on a new digit here. Okay. Does this converge to anything? And you would say, by the monotonic convergence theorem, yes, it does, because I can see that all these terms are bounded by 1.5. Right? All these terms are bounded by 1.5, and every time you're adding on a number, you're making the sequence get a little bit bigger. Right? So this is an increasing sequence, right? 1.4, 1.41, 1.414. Right? It's an increasing sequence and has an upper bound. So I know that there's going to be some limit to it. That's how one uses it. Okay, and we'll use it in another in the next class to show what 2 to the pi means. Say, right? What does 2 to the pi mean? What does 2 to the pi mean? Okay. So it's not clear at this point, but yeah,
I was
Gwyneth.
going to ask about pi, but.
Yeah, same thing for pi, right? Pi is this number, right? Is there an actual real number that is called pi? Well, by the monotonic convergence theorem, yes, there is. Okay. Right? If somebody gave you, this sequence 3, 3.1, 3.1, 4, etc., right? And you say, does this converge to anything? And you say, well, it has to. It has to because it's bounded above and it's increasing. It's an increasing bounded above sequence, and so by this mysterious property of the real numbers, we know that there's a real number that actually is the limit. I may as well talk about 2 to the pi. I may as well talk about irrational exponents at this point because it makes sense, and we have probably enough time to do it. Right? What's 2 to the 3? Well, you know what 2 to the 3 is, right? It's just 8, right? What's 2 to the 3.1? If I asked you what's 2 to the 3.1, how would you calculate it? What does that mean to you, 2 to the 3.1? Stefan? Victor?
2, hold on.
Could you do 2 to the 3 plus 2 to the 0.1?
You could do it that way. You could say 2 to the 3 times 2 to the 0.1, where 2 to the 0.1 is 1/10, right?
Yeah.
Right. So 2 to the 3 times 2 to the 1/10 to the 10th. 2. Yeah, it's 8 times the 10th root of 2, right? And you could keep on going like that. Right. The same thing as 2 to the 31 tenths. Right. And then 2 to the 3.14, right, it's going to be 2 to the 3 times 2 to the 1/10 times 2 to the 4 100ths. Right. And you see that this is how does one define this? Well, you look at the sequence and you say, this, so what does this mean? Observe that this sequence is increasing and bounded above. right? It's increasing because every time you're multiplying by something bigger than 1.
It's bounded by 3.2.
And it's bounded by
Or
2 to the 3.2, right? Bounded above by 2 to the 3.2. Right? Or 2 to the 4 if you want to be reckless. Okay. So the monotonic convergence theorem says there's a limit. Right? 2 to the pi, that limit we call, which we call 2 to the pi. Okay, so that's what 2 to the pi means. 2 to the pi is the limit of the monotonic increasing sequence that you get by looking at this the thing to the powers of increasing accuracy. Okay, so that's how you get irrational exponents, which you didn't have before. Okay. Okay, that's it for today.